In the first decade of the 20th century, American physicist Robert Millikan performed a series of experiments with the goal of finding the charge of an electron. Using a simple apparatus, he pitted electrical forces on charged oil droplets against gravitational forces. From his experiments, he was able to determine the charge of an electron to within less than 1% error. Later experiments produced a value closer to what is accepted today. Before Millikan, at the end of the 19th century, scientists knew that atoms were not the smallest units of matter, but were composed of smaller particles. J. Thompson conducted a series of experiments with cathode ray tubes, proving the existence of one of these smaller particles, the electron. By adjusting the magnetic and electric fields within the cathode ray tube, he calculated the mass-to-charge ratio, or m/e, of the electron. Adjust the position of the magnets and the strength of the electric field to view the response of the electron beam. Thompson was unable to provide a value for either m or e, but if the value of one is determined, the other can be calculated using this ratio. Millikan set out to find the charge of an electron using this apparatus. It operates as follows. 1. An atomizer produces fine oil droplets. 2. The oil droplets fall through a hole in the first chamber as a stream of tiny droplets. 3. X-rays negatively charge the oil droplets. 4. An applied voltage on two plates surrounding the oil droplets creates an electric field. The electric force pulls some droplets upward. 5. The rate at which the oil droplets are falling and rising between the two charged plates is measured through a microscope. In the lower chamber of Millikan's apparatus, initially oil droplets fall between two uncharged plates. Droplets that are the same size fall at the same speed. Even after the droplets have a charge on them, they will fall at the same rate as long as they are not in an electric field. Now we will apply a voltage. In this sample, all droplets are the same size but have different amounts of charge. The darker orange droplets have more charge than the lighter orange droplets. Try it yourself. Use the dial to adjust the voltage on the plates in the chamber to see how an electric field affects the droplets. The drop will travel upwards or downwards at a constant velocity depending on the forces acting upon it. With no electric field, the droplet reaches terminal velocity when the downward force from gravity is equal to the upward force from air resistance. V0, the terminal velocity, equals -k, which is a constant based on air resistance, times m, which is the mass of the drop, times g, which is acceleration due to gravity. When a large electric field is applied, the electric force on the droplet is larger than the gravitational force and acts in the opposite direction. The droplet switches direction and moves upwards. Air resistance now acts in the downward direction. The net force on the droplet is the sum of the gravitational force, air resistance, and the electric force. V1, the terminal velocity, equals k, which is a constant based on air resistance, times the quantity EQ, which is the electric field strength, minus m, which is the mass of the drop, times g, which is acceleration due to gravity. When analyzing the differences between velocity measurements for drops with the same mass, a trend emerges. Each difference is 49 microns per second, or a multiple of 49 microns per second. 147 microns per second divided by 49 microns per second equals 3. Delta V equals n times 49 microns per second, where n is a whole number. Velocity is related to charge through V1 equals k times the quantity EQ minus m times g. So, if the velocities of the droplets are multiples of a discrete amount, then the charge on each droplet must also be the multiple of a discrete amount. This smallest discrete value of charge is E, the charge of an electron.